Express 3y squared minus 12y minus 15 in the form 3 times y plus a all squared plus b, where a and b are constants. Okay, so we've got a quadratic 3y squared minus 12y minus 15, which is in standard form, and we're required to express it in turning points form. So we'll be completing the square. So the first step in completing the square is to ensure that the coefficient of the square term is 1. So we're going to divide each term by 3. We get 3 times y squared minus 4y minus 5. Then add a bracket squared and subtract that same bracket squared. The content of the bracket is half the coefficient of the middle term, so half of minus 4 is minus 2. The first 3 terms form a perfect square trinomial, so we'll have y minus 2 all squared, and we can evaluate the last 2 terms, so minus 5 minus 4 will be minus 9, and we can now bring 3 into the square bracket, so 3 times y minus 2 all squared minus 27. A is therefore minus 2 and b is minus 27. Hence find the exact solutions of the equation 3x to the 4 minus 12x squared minus 15 equals 0. So the quadratic we start off with is 3y squared minus 12y minus 15 equals 0. And we now need to find the solution to the quadratic 3x to the 4 minus 12x squared minus 15 equals 0. I call it a quadratic because it's a quadratic within a quadratic. So we continue to see that what's different between the two expressions is that we've replaced y with x squared. So the solution to 3y squared minus 12y minus 15 would be, well, first we're going to simplify this quadratic as y squared minus 4y minus 5 equals 0. And then solve for y. So y plus 1 minus 5, so y equals minus 1, or y equals 5. And then to solve 3x to the 4 minus 12x squared minus 15 equals 0, we simply equate y to x squared. So x squared equals negative 1. This has no solution, since x squared is always a positive number. Or x squared equals 5. So x equals plus or minus the square root of 5. And that is the solution. Question 2. The diagram shows two curves. One curve has an equation y equals sin x, and the other curve has equation y equals f of x. In order to transform the curve y equals sin x to the curve y equals f of x, the curve y equals sin x is first reflected about the x-axis. We are required to describe fully a sequence of 2 further transformations which are required in order to obtain the function y equals f of x. So the curve y equals sin x is this curve over here, which we know because y equals sin x has an amplitude of 1, which is that height over there, and the function passes through the origin, and at 90 degrees, or rather pi by 2, the function has a value of 1. Sin pi by 2 equals 1. So that's how we identify that this function is y equals sin x, which we're going to call f of x, so that we can then describe the transformed curves, or at least the transformations that give us y equals f of x. So y equals f of x is obviously the other function. Now, to obtain y equals f of x from y equals sin x, in fact I shouldn't have called this f of x, we'll call this function g of x because we are leading to this function y equals f of x. So we first reflect g of x about the x-axis. So a reflection about the x-axis means we change the sign of y. So if the new function is h of x, if the reflection about the x-axis is h of x, then h of x will be minus g of x. So h of x is going to be minus sine x. So if we take the function g of x and we reflect it about the x-axis, we are just changing the sign of y. So every single point on g of x will just have the negative y value. So the first point would be 0, 0. At pi by 2, we have a y value of 1 on g of x. So the y value at pi by 2 for h of x will be at negative 1, just the opposite sign of that. At pi, y will be 0. For g of x, at 3 pi by 2, the y value is negative 1. So the opposite sign will be positive 1. So the next point would be 3 pi by 2, 1. At 2 pi, we'll have a y value of 0. For g of x, at 5 pi by 2, we have a y value of 1. So with the same x value, we'll have a y value of minus 1 for h of x. At 3 pi, we have a y value of 0. At 7 pi by 2 for g of x, we have a y value of minus 1. So for the same x value, we'll have a y value of 1. And then we'll have at 4 pi a y value of 0. So just going to draw in h of x. We're now going to take h of x and transform it, apply two more transformations to get the curve of f of x. So if we just look at the points on h of x and the points on f of x, if we just look at the origin, when x equals when x equals 0 on h of x, the y value is 0. For f of x with the same x coordinate of 0, we have a y coordinate of minus 2. At pi by 2 for h of x, we have a y value of minus 1. And for pi by 2 for f of x, we have a y value of minus 5. Now, because we're required to describe two more transformations, we can't describe this in a single transformation. So we can't simply say that it's a translation. First of all, these 2 points. So the first point where x equals 0, y equals 0. So translate that 2 units down, and at the point 0 minus 2. The next point at pi by 2 has a y value of minus 1. Translate that 2 units down, we'll have a point pi by 2 minus 3. At pi on h of x, we have a y value of 0. Translated 2 units down, the point will be pi minus 2. At 3 pi by 2, we have a y value of 1. Translated 2 units down, we'll have a y value at negative 1. At 2 pi, we have a y value of 1, of 0 rather. Translated 2 units down, the point will be 2 pi minus 2. At 5 pi by 2, we have a y value of minus 1. Translated 2 units down, the y value will be at minus 3. 3 pi, the y value is 0. Translate 2 units down, the y value is minus 2. At 7 pi by 2, the y value is 1. Translate 2 units down, the y value is at negative 1. And where x equals 4 pi, the y value is 0. Translate 2 units down, the y value is at minus 2. So we can now draw a new curve which we will call j of x, and this is a vertical translation of 2 units down of h of x. So j of x is h of x minus 2. J of x equals minus sine x minus 2. This is now the first transformation of h of x. We now need to transform it to f of x. So just looking at the amplitude of j of x, we can see that the amplitude is 1, and for f of x, that amplitude is 3 units. So whichever way you want to look at it, -2 to -5 or 1 to -2. So the amplitude of j of x is -1. The amplitude of f of x is -3. That means that we have a vertical stretch of j of x by a scale factor of 3 to give us f of x. In other words, f of x, f of x. In other words, f of x equals -3, 3 times sine of x. It's scale factor of 3 of minus sine x, and then translated 2 units down. So f of x is -3 sine x minus 2. So the full transformation from h of x to f of x. The first thing we do is we apply a vertical stretch. So the first transformation is a vertical stretch with a scale factor of 3. And once we've done that, we then apply the translation of 2 units down the y-axis. So it's going to be a vertical, rather a translation by the vector 0, -2. Find f of x in terms of sine x. Well, this is just a function we've just obtained. So f of x equals -3 sine x minus 2. Question 3. Coefficient of x cubed in expansion 3 plus ax to the power of 6 is 160. Find the value of the constant a. Now, since we're looking only for coefficients, or at least we've been given information relating to the coefficient of x cubed, we are not going to expand this binomial completely, only as far as is necessary. So we're just going to write out the first few terms. 6 choose 0 times 3 to the 6 of the first term. Then we have 6 choose 1 times 3 to the 5 times ax plus 6 choose 2 times 3 to the 4 times ax squared plus 6 choose 3 times 3 cubed times ax cubed. We can carry on expanding, but we don't need to because we only require the coefficients for x cubed. The terms thereafter, after this term, will contain greater powers of x. So all we're interested in here is the coefficient of x cubed. So this is the only term we are actually interested in. So 6 choose 3 times 27 times a cubed, x cubed, the coefficient, which is that expression over there, equals 160. So 6 choose 3 is 6 times 5 times 4 over 3 times 2 times 1 times 27 a cubed. This coefficient equals 160. So 120 over 6 is 20 times 27 will be 540 a cubed, and that equals 160. A cubed equals 160 over 540, which equals 8 over 27. So therefore a is the cube root of that, which will be 2/3. Hence find the coefficient of x cubed in expansion 3 plus ax to the power of 6 times 1 minus 2x. Now we've already established the first 4 terms of 3 plus ax to the 6, which are these 4 terms over here. Now, when we multiply this entire expression by 1 minus 2x, we are looking for the coefficient of x cubed. So if we just start with the 4th term over here, we will multiply determine x cubed by 1 minus 2x. Now, we will get an x cubed when we multiply by 1. It will get a term in x to the 4, but that doesn't matter. We're looking for terms in x cubed. When we multiply the first term, 6203 to the power 6, by this binomial 1 minus 2x, we're not going to get a term in x cubed. So we can actually disregard that term completely. When we multiply the second term, 6213 to the power of 5 times ax by 1 minus 2x, the most we're going to get is at least the highest degree of x will be the second degree, so we won't get a term in x cubed. We can disregard that term as well. However, the third term here has a term in x squared, and we multiply by this term minus 2x, we will get a term in x cubed. So we are interested in this term, and we are also interested in the fourth term of that expansion of 3 plus ax to the power of 6. So we're going to take these two terms here, 6 choose 2, 3 times 3 to the 4 is 81, times a squared x squared, plus 6 choose 3 times 27 a cubed x cubed, and we're going to multiply that by 1 minus 2x. Now all we're interested in here are the terms in x cubed. So now we're only interested in the terms that will give us a term in x cubed. So when we multiply the first term of the first bracket by the first term of the second bracket, we're not going to get a term in x cubed. So we can disregard that. When we multiply the first term of the first bracket with the last term of the second bracket, we will get x squared times x. So we are going to get an x cubed term. So we'll have 6 choose 2, and we'll evaluate this just now, times a squared x squared, and we're going to multiply that by minus 2x. Then we have the inners, which will give us a term in x cubed, so we are interested in that. So 6 choose 3 times 27 a cubed x cubed times 1 is just what it is. And then we multiply the outer terms, we're going to get a term in x cubed, and we're not interested in that. So we just need to evaluate these terms. Yeah, so 6 choose 2 is going to be 6 times 5 over 2 times 1 times 81. We have a minus sign, so we'll have a minus there, times 2, and then a squared x cubed plus 6 choose 3 is 6 times 5 times 4 over 3 times 2 times 1 times 27 a cubed x cubed, and that will give us minus 2430 a squared x cubed plus 540 a cubed x cubed. So the coefficient of x cubed in this expression here is minus 2430 a squared plus 540 a cubed, and we've already established that a is 2/3, so that will equal minus 2430 times 2/3 all squared plus 540 times 2/3 all cubed equals minus 920. Question 4. The equation of a curve is 1 equals f of x, so f of x equals 2x minus 1 times the square root of 3x minus 2 minus 2. The origin points lie on the curve. Non-exact values have been given correct to 5 decimal places. So we've got points A, B, C, D, E, and F. We're required to find the value of k correct to 5 decimal places. Okay, so to find the value of k, we're simply going to substitute point B into the function f of x. So we're going to evaluate f of 2.0001, which equals 0.00063. This is the value of k. Next, we're required to find the gradient of a chord AE correct to 4 decimal places. So we have the point A, to 4, point E, 2.1, 4.63566. So the gradient of AE will be y2 minus y1 over x2 minus x1. So that'll be 4.63566 minus 4 over 2.1 minus 2, which equals 6.3566. Finally, we're required to deduce the value of f prime 2 using the values in the table. So if we just take a closer look at this, we have points A, B, C, D, E, and F, and each of the points form a chord with A, and we've got the gradient of each of those chords. So the gradient of chord AB 6.2501, the gradient of chord AC 6.2511, of AD 6.2608, AE 6.3566, and AF 7.2288. So it would be very difficult, at least it would be a lot easier to plot these points. It's not entirely necessary, but it will be much easier to conceptualize and visualize the problem if we plot the points A, B, C, D, E, and F on a Cartesian plane to see what is actually happening here. So we're going to do that. So by plotting points A through to F, the difference in x values is very, very small. So you're not going to see it clearly on this graph. The first point here will be A, which is the point 2, 4, and the last point up here is the point F, which is 3, 11.22876. Now, as the point F, if we start at point F and we move down this curve towards point A, we are going to approach the gradient of the tangent, right? Since every point on this curve, we have A, B, A, C, A, D, A, E, A, F, we can draw chord AF quite clearly, but with the other points, it will be increasingly more difficult to see because of the small magnitude of the coordinates. The gradient between any 2 points on a line would be a fixed gradient, y2 minus 1 of x2 minus x1. On a curve, however, we have an average gradient, right? Because the gradient between any 2 points on a curve is never the same. So we talk about an average gradient. So as f approaches A, the gradient of the secant AF will approach the gradient of the tangent at point A to the curve. So you can clearly see that the gradient of AF is 7.2288. Then as f approaches point E, the gradient is 6.3566. The gradient of AE is 6.3566. E then gets even closer to A and reaches point D, so the gradient of AD 6.2608. D gets closer to A at point C, the gradient of chord AC 6.2511, and then C gets even closer and approaches point B, the gradient of AB 6.2501, and then B will approach A and get even closer to point A. So as the points from F through to B get closer and closer to point A, the gradient of the secant line approaches the gradient of a tangent at point A. So we can clearly see that we've gone from a gradient of 7.2288 to a gradient of 6.25019. Now if we just look at the gradient of AB and the gradient of AC, the gradient of AC is 6.2511 and the gradient of AB is 6.2501. So it stands to reason that the gradient at point A, so the gradient of a tangent at point A would approach 6.25. And that's what we're looking for. So the gradient, so f prime x, which represents the gradient of a tangent to a curve. F prime 2 is the gradient of a tangent to a curve at the point where x equals 2. So where x equals 2, we have the point A. So we are talking about the gradient of a tangent to the curve at the point A. So f prime 2 would therefore equal 6.25. Question 5. Prove that density is sine squared x minus cos x minus 1 over 1 plus cos x equals minus cos x. As with all trigonometric identities, proving trigonometric identities, you generally only need to manipulate one side of the equation to make it equal to the other side. And you always start with the more complex side of the equation. So in this case, we're going to start with the left-hand side. Now, bear in mind that we are trying to get to a single trig ratio minus cos x. So the fact that we've got sine x and cos x on the left-hand side, we're going to have to write the sine squared in terms of cos. So sine squared will be 1 minus cos squared x minus cos x minus 1 over 1 plus cos x. We can just clean this up a bit. So we'll have minus cos squared x minus cos x, then we have 1 minus 1, which is 0, divided by 1 plus cos x. In the numerator, we can now factorize and take out a common factor of minus cos x, and we are left with cos x plus 1 over 1 plus cos x. Cos x plus 1 is the same as 1 plus cos x, so the division of that will give us 1, which means we're left with minus cos x, which equals right-hand side. Hence, solve the equation sine squared x minus cos x minus 1 over 2 plus 2 cos x equals a quarter, for x is an angle between 0 and 360 degrees. Okay, now we have just shown that the expression sine squared x minus cos x minus 1 over 1 plus cos x equals minus cos x. So we have the numerator being the same, however the denominator is slightly different. So we are going to take a common 2 out of this denominator. Sine squared x minus cos x minus 1 over 2 plus 2 cos x equals sine squared x minus cos x minus 1 over 2 times 1 plus cos x. Now, this expression here is minus cos x. So we will have minus cos x, and this 2 is in the denominator, so minus cos x over 2. And we are told that this expression equals a quarter. So a quarter equals minus cos x over 2. So we can just cross multiply here. And we'll have 2 equals minus 4 cos x. Cos x equals minus a half. We now have a simple trigonometric equation which we can solve. The reference angle will be 60 degrees. The fact that this ratio is negative just means that the solution lies in a quadrant where the ratio cos is negative. Cos is positive in the first and the fourth, which means it's negative in the second and the third. And the domain is x is an angle between 0 and 360 degrees. So the first solution will be in the second quadrant, which is 180 minus. So it will be 180 minus 60 degrees. So x equals 120 degrees. That's the one solution. Or the second solution will be in the third quadrant, 180 plus theta, or in this case 180 plus 60. So x equals 240 degrees. So x is either 120 degrees or 240 degrees. The function f is defined by f of x equals 2 over x squared plus 4 for x is less than 0. Diagram shows the graph of y equals f of x. We're required to sketch on the same set of axes the graph of the inverse function of f, showing any relevant mirror line. Now, the inverse of any function is a reflection about the line y equals x. So we're just going to put in the line y equals x. Now we don't really need any of the points, we just have to try and sketch this to the best of our ability. So the function will look something like that. The inverse of the function f of x equals 2 over x squared plus 4 for x being less than 0 is the function g of x equals minus the square root of 2 over x minus 4. To find an expression for the inverse of f, we are going to switch the x and the y values around. So to find the inverse of f, we will have x equals 2 over y squared plus 4, and now we make y the subject of the formula. So x minus 4 equals 2 over y squared equals 2 over x minus 4, y therefore equals the square root of 2 over x minus 4. But because the domain for f of x is less than 0, we must have y being negative for the inverse function. So y will equal minus the square root of 2 over x minus 4. And this is the inverse function of f. F of x and g of x are reflected about the line y equals x. Next, we're required to solve the equation f of x equals 4.5. So 2 over x squared plus 4 equals 9 over 2, which is 4.5. The LCM is 2x squared. So we'll have 4 plus 8x squared equals 9x squared. X squared minus 4 equals 0. X plus 2 times x minus 2 equals 0. X equals minus 2 or x equals 2. Because x is less than 0, x equals 2 is not applicable. So the only solution is x equals minus 2. Next, explain why the equation the inverse of f equals f has no solution. Now to answer this, we're going to look back at the sketch graph of f and of the inverse of f. Now we can clearly see from the sketch graph of these that there is no point of intersection, so therefore there is no solution. Right? So the simple answer is no point of intersection between f and f to the minus 1. Question 7. In the diagram, AOD and BC are two parallel straight lines. Arc AB is part of a circle with center O and radius 15 centimeters. Angle BOA is theta radians. Arc CD is part of a circle with center O and radius 10 centimeters. Angle COD is pi by 2 radians. Show that theta equals 0.7297, correct to 4 decimal places. Okay, so we have O being the center of sector OCD. So OC is also 10 centimeters. So that's the OC and OD are the radii of sector OCD. Sector ABO has OB also being 15 centimeters. AO and BO both equal 15. OC equals OD, which is 10. Angle BOC we will call alpha. Alpha plus theta in degrees will be 90 degrees. But in radians, alpha plus theta will be pi by 2. So alpha will be pi by 2 minus theta. Now we can find a trigonometric ratio involving alpha on the sides 15 and 10 centimeters. So before we do that, because BC is parallel to AOD, we know that angle BCO is also 90 degrees since it equals angle COD. So relative to alpha, OC, which is 10 centimeters, is the adjacent side, and OB, which is 15 centimeters, is the hypotenuse. So 10 over 15 will be adjacent to our hypotenuse, which is cos alpha. So cos alpha is 10 over 15, and then alpha will therefore equal, just make sure you're working in radians. Alpha is 0.8411, correct, 2, 4 decimal places. Therefore, theta will be pi by 2 minus alpha. That will be pi by 2 minus 0.8411. So theta equals 0.7297 radians. Let's find the area. The area of ABCD equals the area of sector AOB plus the area of triangle BOC plus the area of sector COD. So the area of sector AOB will be a half the radius squared. The radius of sector AOB is 15, so it's going to be a half 15 squared times the arc angle theta, which is 0.7297, plus the area of right angle triangle BOC is half base times height, so it's half BC times OC, so it's half 5 root 5 times 10, plus the area of the sector COD is a half the radius squared times the arc angle. The radius of sector COD is 10, so it's going to be a half, the area is a half 10 squared times the arc angle of sector COD, which is pi by 2. So the area of ABCD is therefore 216.5 centimeters squared, which correct to 3 significant figures is 217 centimeters squared. The first 3 terms of an arithmetic progression are 25, 4p minus 1, and 13 minus p, where p is a constant. Required to find the value of the 10th term of the progression. So given that the first 3 terms of the progression of an arithmetic progression, there's a common difference between successive terms. So 4p minus 1 minus 25 equals 13 minus p minus 4p minus 1. 4p minus 26 equals 13 minus 5p plus 1. So 9p equals 40. So p will be 40 over 9. So the first 3 terms of the sequence will be 25, 151 over 9, and 77 over 9. A is obviously 25, and common difference minus 74 over 9. The 10th term therefore equals 25 plus 9 times minus 74 over 9. That's 25 minus 74. So the 10th term equals minus 49. The first 3 terms of a geometric progression are 25, 4q minus 1, and 13 minus q. The q is a positive constant. Find the sum to infinity of the progression. So given the first 3 terms of a geometric progression, there's a common ratio between successive terms. So 4q minus 1 over 25 equals 13 minus q over 4q minus 1. Cross multiplying, 4q minus 1 all squared equals 25 times 13 minus q. 16q squared minus 8q plus 1 equals 325 minus 25q. Using the quadratic formula, we get q equals 4, or q equals minus 5.0625. Now q cannot be anything but a natural number, so this will not be applicable. So q equals 4, so the sequence will be 25, 4 times 4 minus 1, 13 minus 4, so the sequence is 25, 15, 9. A equals 25, and the common ratio will be 3/5. The sum to infinity equals a over 1 minus r, that equals 25 over 1 minus 3/5, which is 25 over 2/5, which is 125 over 2. Question 9. The diagram shows part of the curve with the equation y equals 1 over 5x minus 4 to the third, and the lines x equals 2.4 and y equals 1. The curve intersects the line y equals 1 at the point 1, 1. We are required to find the exact volume of the solid generated when the shaded region is rotated through 360 degrees about the x-axis. Okay, so the shaded region that is going to be rotated about the x-axis is bounded by the curve y equals 1 and the curve y equals 1 over 5x minus 4 to the third. That means we have a disk washer model. So we have an inner radius of 1 over 5x minus 4 to the third, and we have an outer radius which is 1. So the volume of the solid obtained by rotating the shaded region about the x-axis would be given as the integral from x equals 1. So this is the line x equals 1 to x equals 2.4. So integrate from x equals 1 to x equals 2.4. The area of the circular cut is pi r squared, so we're going to have pi. The outer radius is going to be 1. We'll just write it as pi times the outer radius squared minus pi times the inner radius squared. So we have the area of the outer circular cut minus the area of the inner circular cut, and that will give us the region we're looking for, and we then integrate this with respect to x, and this dx represents the thickness of each circular cut. So we'll have area times thickness, or area times height, which gives us volume. So we can take out the pi out of the integral as it's a constant. So we'll have pi times the integral from x equals 1 to x equals 2.4. The outer radius squared will be 1 squared, which is just 1, minus the inner radius squared will be the square of 1 over 5x minus 4 to the third. So we're just going to write that as 5x minus 4 to the minus a third, and we're going to square that to give us the inner radius squared, and all of this is integrated with respect to x. Integrating the expression gives us pi times, integrating 1 with respect to x is just x, minus the integral of 5x minus 4 to the minus 2/3 is 5x minus 4. We're going to add 1 to minus 2/3, which will give us a third. We then divide by a third, so we're multiplying by 3. So we'll just write it as division by a third, and we also multiply by 1 over the derivative of 5x minus 4. So we can multiply by 1 over 5. And this is evaluated between x equals 1 and x equals 2.4. 4 pi by 5 units cubed. And that's the volume of the shaded region when it is rotated about the x-axis. Question 10. The equation of a circle is x minus 3 all squared plus y squared equals 18. The line of the equation y equals mx plus c passes through the point 0 minus 9 and is a tangent to the circle. We're required to find two possible values of m For each value of m, find the coordinates of the point at which the tangent touches the circle. Now, as with most analytical or coordinate geometry problems, it is strongly suggested that you draw a sketch. Right? The sketch is going to help you conceptualize and visualize the problem, and you'll know exactly, you'll have a better idea how to start and approach the problem. Okay, so we've got the circle here. Point over here, A, is the point 0, minus 9, and the straight line passing through that point is a tangent to the circle. So we can call that point B. Also, have another straight line passing through point A, a tangent to the other side of the circle, and this point we call C. So we're required to find essentially the equations of these two tangents to the circle. The center of the circle, which we'll call M, is the point 3, 0. So, since AB and AC are tangents to the circle, there's obviously only one point of contact. So given that a line y equals mx plus c passes through A, point 0, minus 9, we know that both of these tangents can be written in this form, y equals mx minus 9. Now, depending on the value of m, we're either going to get tangent AB or we're going to get tangent AC, but that's what we're looking to find. So the best approach to finding the value of m is to equate the circle to this line over here. So we're going to substitute mx minus 9 in for y. We're now going to expand this out and get a quadratic equation from which we're going to determine the discriminant. The reason we're going to find the discriminant is that the straight line is a tangent to the circle. That means there's one point of intersection, which means that the value of the discriminant will be 0. So that's where we're going to start. So x squared minus 6x plus 9 plus m squared x squared minus 18mx plus 81 equals 18. We're now going to find the discriminant for this expression, which equals minus 6 minus 18m whole squared minus 4 times a. A is coefficient of x squared, so it's going to be 1 plus m squared times c, which is 72. Now, because the straight line is a tangent to the circle, there's only one point of intersection. So, in other words, roots delta equals 0. So 36m squared plus 216m minus 252 equals 0. We can divide through by 36. So m squared plus 6m minus 7 equals 0. M minus 1, m plus 7, m equals 1 more, m equals minus 7. That means that the equations of these tangents, tangent AB will be y equals x minus 9, and tangent AC, the equation will be y equals minus 7x minus 9. To calculate the coordinates of the point at which the tangent touches the circle, we are going to equate the tangent each tangent in turn to the circle. So x minus 3 all squared plus x minus 9 all squared equals 18. X squared minus 6x plus 9 plus x squared minus 18x plus 81 equals 18. 2x squared minus 24x plus 72 equals 0. X squared minus 12x plus 36 equals 0. X minus 6 times x minus 6 equals 0. It should not be surprising that we get a single value of x because we have a tangent touching a circle, so there's only one point of intersection. Y equals x minus 9 is the equation of the tangent, so y equals 6 minus 9, which is minus 3. So the point of intersection B will be 6 minus 3. And then to find the other point of intersection, we're going to take the other tangent and equate it to the circle. So equating the tangent y equals minus 7x minus 9 to the circle gives us quadratic 50x squared plus 120x plus 72 equals 0. We can divide through by 2, so 25x squared plus 60x plus 36 equals 0. And this factorizes as 5x plus 6 times 5x plus 6, and that equals 0. X equals minus 6 over 5, or x equals minus 6 over 5, and that shouldn't be surprising again that we have one x values because we have one point of intersection. So the y-coordinate of the point of contact between the tangent and the circle is minus 7 times minus 6 over 5 minus 9. That equals minus 3/5. So point C will be minus 6 over 5 minus 3 over 5. Question 11. A function is defined by f of x equals 4 over x cubed minus 3 over x plus 2, for x does not equal 0. We're required to find the set of values of x for which f of x is decreasing. Now, the function f of x will be decreasing when the first derivative function, or the gradient function, is less than 0. And conversely, the function will be increasing when the derivative function is greater than 0. So we need to firstly find an expression for f prime x, and then we need to show, or rather find the set of values of x for which that function is decreasing. So once we've found the expression for f prime x, we are then going to make it less than 0 because we're looking for all values of f prime x that are negative in order for the function to be decreasing. So we need to find the set of x values for which f prime x is less than 0. We can now differentiate f of x. So f prime x will give us minus 12x to the minus 4 plus 3x to the minus 2. The derivative of a constant is 0. We're just going to write this in a neater form. F prime x equals minus 12 over x to the 4 plus 3 over x squared. To find the values which the function f of x is decreasing, the first derivative must now be negative, must be less than 0. So minus 12 over x to the 4 plus 3 over x squared must be less than 0. Since x cannot be 0, we can multiply through by x to the power of 4 to remove this denominator. So we'll have minus 12 plus 3x squared is less than 0. 3x squared minus 12 is less than 0. X squared minus 4 is less than 0. X plus 2 times x minus 2 is less than 0. So our critical values are x equals minus 2 and x equals 2. If we just draw the quadratic function y equals x squared minus 4, we'll have our critical values of minus 2 and 2. The coefficient of x squared is positive, so the function is going to shape up. And we're looking for negative y values, so we are looking for x values where the function lies underneath the x-axis, which is this blue shaded region, and that the x values in this region are between minus 2 and 2. So if x is less than 2 but greater than minus 2, then this function f of x will be decreasing. The triangle is bounded by the y-axis, normal to the curve at the point where x equals 1, and the tangent to the curve at the point where x equals minus 1. We're required to find the area of this triangle correct to 3 significant figures. Okay, so we're first going to have to find this triangle, right, by finding the point on the curve where x equals 1 and where x equals minus 1. So to do that, we're going to substitute 1 and minus 1 into f of x. So f of 1 will give us 4 over 1, 4 minus 3 over 1, 3 plus 2, which is going to be 3. So we have a point 1, 3 on the curve. We'll call that point A. And f of minus 1 will be 4 over minus 1 cubed, so that's minus 4, minus 3 over minus 1, so that'll be plus 3, plus 2, and that will give us 1. So we'll have the other point being B, minus 1, 1. So we're just going to estimate where these points are. 1, 3. We can just estimate it is here, so that'll be point A, and 1 minus 1, 1. Let's say that it's over here, and that will be point B. So we now have a normal to the curve at point A. So if we first draw a tangent line at A, then the normal to the curve at A will be perpendicular to this tangent. The yellow line will be the normal to the curve at point A. And then we also have a tangent to the curve at the point where x equals minus 1. So at point B, we have a tangent to the curve. And now a triangle is bounded by this normal and this tangent and the y-axis. So we now have this shaded area for which we need to find the area. Now to find the area of this triangle, we are going to be using the area rule. It's not a right angle triangle, which is quite evident. So we are going to need to find two sides of this triangle and the size of the included angle. So the point of intersection of the normal and the tangent we'll call point C. So the first thing we need to do is find the coordinates of C. Now to find the coordinates of C, we'll need to find the equation, the defining equation of the tangent and that of the normal, equate the two to find the coordinates of C. Once we have the coordinates of C, we'll obviously have the defining equation of the normal, which means we can find the coordinates of this point we'll call D, which is the y-intercept of the normal. We can also find the y-intercept of the tangent, because we'll have the defining equation of the tangent, we'll call that point E. And then once we have the coordinates of C, D, and E, we can then determine the length of the sides of the triangle. So that's a starting point. So to determine the equation of the normal, normal is obviously a straight line, and the defining equation of a straight line is y equals mx plus c. So we need to determine the gradient of normal, and we need one point. Now, the point that lies on the normal is point A, so we've got the point. We need to determine the gradient of AC. Now, to get the gradient of a normal, we first need to determine the gradient of the tangent to the curve at that point. So we are going to find the gradient of the tangent to f of x at point A. So to find the gradient of a tangent to a curve, we're going to differentiate the curve. Now, the derivative function is given by f prime x equals minus 12 over x to the 4 plus 3 over x squared. At point A, the x value is 1. So f prime 1 will be minus 12 over 1 to the power of 4, still minus 12, plus 3 over 1 plus 3. So the gradient of the tangent to the curve at the point A will be minus 9. This is the gradient of the tangent to the curve at point A. The gradient of the tangent to the curve at A is minus 9. So the gradient of the normal to the curve at point A will be the reciprocal of the gradient of the tangent, will be 1 over 9 with opposite sign, so it will be positive 1 over 9. We now have the point 1, 3 and the gradient of the normal. We can now determine the equation of the normal. We can also use y equals mx plus c. It's just far quicker to use. Y minus y1 equals m times x minus x1 to find the equation of a straight line. So y minus 3 equals 1 over 9 times x minus 1. Y equals 1 over 9x minus 1 over 9 plus 3. So the equation of the normal is given by y equals 1 over 9x plus 26 over 9, which you can also write as 9y equals x plus 26. This now represents the equation of the normal to the curve f at the point A. Similarly, to find the equation of the tangent to the curve at the point minus 1, 1, which is the point B, the derivative function f prime x is minus 12 over x to the 4 plus 3 over x squared. So this represents the gradient of a tangent to the curve. So to find the value of the gradient of the tangent to the curve at B, we substitute x equals minus 1. And that will give us minus 12 over minus 1 to the power of 4, so it will be minus 12, plus 3 over minus 1 all squared will still be plus 3, which is minus 9. Now, the fact that we get a gradient of minus 9 just means that this diagram is not drawn accurately. So that shouldn't throw you off. The gradient of the tangent is minus 9. The gradient of the tangent to the curve at B is minus 9. The point B is minus 1, 1. So we can determine the equation of this tangent at B. So y minus y1 equals m times x minus x1. Y minus 1 equals minus 9 times x plus 1. Y equals minus 9x. That will be minus 9 plus 1 is minus 8. So y equals minus 9x minus 8 is the equation of the tangent to f at point B. Now that we have the defining equation of the normal to the curve at A and the tangent to the curve at B, we can equate these two lines to get the coordinates of point C. So 9 times, substituting minus 9x minus 8 in for y, we'll have 9 times minus 9x minus 8 equals x plus 26, minus 81x minus 72 equals x plus 26. 82x equals minus 98, so x equals minus 49 over 41. Need to find the coordinates, the y coordinate of point C. We substitute its x coordinate into either of the two straight lines. So y equals minus 9 times minus 49 over 41 minus 8. Y equals 113 over 41. So C is the point, minus 49 over 41, 113 over 41. So we have the coordinates of point C. We also need the coordinates of point D and of point E, which are respectively the y-intercepts of the normal to the curve at A and the tangent to the curve at B. So to find y-intercepts, we put x equal to 0. So the normal line, the normal to the curve at A, is equation 9y equals x plus 26. So when x equals 0, we will have 9y equals 26. Y is 26 over 9. So D is the point 0, 26 over 9. Similarly, to find the coordinate of point E, E being the y-intercept of the tangent to the curve at B, we put x equal to 0 for the equation, the defining equation of the tangent to the curve at B, which is given by y equals minus 9x minus 8. So when x equals 0, y will be minus 8, which means that E is the point 0 minus 8, which just further confirms that the diagram is not drawn accurately. We can now determine the length of CD, DE, and CE using the distance formula. So we'll start with CD. That would be the square root of 0 minus 49 over 41 all squared. So 0 plus 49 over 41 all squared plus 26 over 9 minus 113 over 41 all squared. So CD equals 1.2025. Proceeding in a similar fashion, the length of CE equals 49 over 41, the square root of 49 and 41 all squared, plus minus 8 minus 113 over 41 all squared. So C equals 10.822. And the length of DE, which is just a vertical line segment, DE will be 26.9 plus 8, which equals 10.889 units. Now that we have the lengths of the three sides of the triangle, we can determine an interior angle. It doesn't matter which angle you choose. We'll just call this angle here, angle CED theta. So to find theta, we're going to use the cos rule. So CD squared equals DE squared plus CE squared minus twice DE CE cos theta 6.34 degrees. We can now determine the area of the triangle, which is a half the product of the two included sides. So for angle theta, that would be CE and DE sine theta. So the area will be 6.507 units r squared. It was approximately 6.51 units squared.